Thank you, Marta. And thank you, Leonardo, also for inviting me to give a talk at this wonderful conference. So before I start, I just want to say that this is a recurrent conference, but this year it's part of a special program on symplectic geometry that we're organizing this semester. So there will be lots of activities later on, and I think many of you are aware of it, especially for the students who are here. I want to promote these events. Next week, we're going to have a mini course on celestial mechanics and symplectic geometry, and then we'll have schools and conferences on different topics. You can check that on the website. But it's a pleasure to talk to you about some of my recent work, which is joint with Jahan Ostrover from Tel Aviv University. So I want to talk a little bit about some symplectic embedding problems and some developments in a specific family of them. So to set up the notation, let me call B2n of C the ball in R2n of capacity C. So this is the set of points Z in R2n such that pi times the norm of Z squared is less than C. So it's like the radius. It's the symplectic radius. So a question that one can ask, sort of a simple, naive question is, given a subset of R2n, what is its Gromov width? So what is the smallest ball that can embed into X? And you can also ask a converse question. So you can ask about when does this ball symplectically embed into X? So that means that there's a smooth embedding from the ball into X, which preserves the standard symplectic structure. So yeah, and you can also ask the converse question. So when does the set symplectically embed into a ball? Okay? So this is a question that's very fundamental, very, in symplectic topology, it's been asked for a long time. The most famous and kind of starting point of this theory, and it's probably the starting point of symplectic topology, was Gromov's non-squeezing, which says the following. So Gromov, in 1985, very important, famous paper, he said, well, if X is the cylinder, so let me define it, as usual, Zn is the ball in dimension 2, and you take the symplectic product with R2n minus 2, then the ball embeds symplectically into the cylinder if and only if the little r is less than or equal to big R. And I'm going to stop writing the S for symplectical embedding. I mean, every embedding I'll write today will be a symplectic embedding. So I'll drop this S from the notation. So this is a very important work. I'm sure everyone here, or most of you here, have heard this before. But I also want to point out that this is if and only if there is an inclusion. So basically, you cannot do better than inclusion. So this is the first phenomenon of symplectic rigidity. So you cannot, symplectic geometry doesn't give you any more flexibility for this particular embedding problem than inclusion. Okay, so this is kind of the strongest rigidity result that you could hope for. Okay, so I'm going to talk about a lot of different kinds of embeddings, and you see that sometimes we get rigidity like this, and sometimes we get a lot more flexibility. Okay, so what's the most natural set, and then the next set that we could look at in R2n? I think that's the ellipsoid. So, kind of a deformation of a ball. So this is I'm going to fix n positive numbers, and I'll define the ellipsoid to be, oh, and I forgot to say, but if you ask the converse question for the cylinder, it doesn't really make sense because the cylinder has infinite volume. So you can't really embed it into a ball, just by volume reasons. Okay, but for the rest of the talk, we'll talk about compact sets. So the infinite volume won't be an obstruction. So let's look at the ellipsoid. So it's similar. So it's the set of, I'm going to write Z1 through Zn. I'll think about my Rn as being Cn. And such that pi times norm of Z1 squared over A plus etc. plus norm of Zn squared A1 and An is less than 1. And notice this is the most general ellipsoid because up to a symplectic transformation, you can make these parameters all the same. And I should actually write down once and for all what the symplectic structure is, just for those who, just to write it down once. So my symplectic structure is dxi dyi, where I think of zi as being the point xi, yi. Okay, so this is the ellipsoid, and we can ask this question, what's the biggest ball that embeds into the ellipsoid, and what's the smallest ball such that the ellipsoid embeds into it? And it turns out this is a very difficult question. Actually, the first question is not difficult. The first question is pretty easy. So it's an easy consequence of the Gromov's non-squeezing that the biggest ball that embeds into an ellipsoid, so this embedding happens if and only if C is less than or equal to the smallest of the numbers A1 through AN. So you can check that this ellipsoid clearly fits into the cylinder with the smallest parameter. And then by that theorem, we have this restriction. So we have strong rigidity here. So this happens if and only if the ball is contained in the ellipsoid. Okay, so this direction is an easy consequence of Gromov's non-squeezing theorem. The other direction, though, is a lot harder. So if you want to find when the ellipsoid embeds into the ball, that's a pretty difficult question that's not even understood in all cases. So the story in dimensions bigger than 4 is a kind of a long story, and there are partial results. There's not a complete understanding yet. But I'll just tell you what for the case n equals 2. And actually, for the rest of the talk, we'll stay in the realm of n equals 2. And I guess there are two reasons for that. Like Joel said in his talk, dimension 4 is when 2 plus 2 equals 4. So you can have intersection theory, which allows you to have, for example, ECH and many other things. And the other big reason is that we have Seiberg-Witten invariance, which is also the reason why one of the reasons why ECH is so powerful. So we have Seiberg-Witten invariance, and we have intersections, and so many of the techniques really only work in dimension 4. So for the rest of the talk, I'll talk about dimension 4. So in dimension 4, let's ask this question. So when does the ellipsoid with parameters A and B embed into the ball with parameter C? So I mean, we can normalize it. Of course, if there is such an embedding, you can always multiply everything by a certain number. So we're actually going to just ask when E1A embeds into BC. Okay, so a few things that one can find, and I think this is basic. This is due to Aubry-Mather. I think Aubry-Mather proved that if A is between 1 and 2, then this happens if and only if, so the embedding exists if and only if C is greater than or equal to A. Okay, so that is basically the strong rigidity. So this is rigidity. So this means that E1A has to be contained in B of C. Okay, so if the ellipsoid is close enough to a ball, so if it's not very pointy, then you have strong rigidity. And he also showed that for A between 2 and 4, so this is one case, and then for A between 2 and 4, actually E1A always embeds into B2. Okay, so if you go all the way to 4, when you get to E14, E14 has the same volume of B2. So he basically said, you go all the way from A equals 1 to 2, and then you have strong rigidity, and then between 2 and 4, you actually fill up the whole volume of that ball. So you can do better and better and better until you fill up the whole volume. Okay? So now, and then the question is, what happens after 4? So you can write down, you can encode this in a function. So I'm going to call that f of a. So this is the infimum of C such that E1a embeds into BC. And now, of course, my balls for the rest of the talk are 4-dimensional balls. So I'm not writing B4 anymore. So what Bursztyn showed is that so that f of a is equal to a if a is between 1 and 2, and its constant equals to 2 if a is between 2 and 4. Okay. And then Macduff and Schlenk computed this function for the rest, for all other a's. And I should also say we don't need to look at a less than 1 because we can just switch the order and then rescale. So we really only care about this function for a greater than or equal to 1. Okay? So Macduff and Schlenk proved in 2009 in an Annals paper. They computed this function. It's really beautiful. So I'll tell you a little bit about this function. So consider the sequence Gn of the odd terms of the Fibonacci sequence. So this is the sequence n greater than or equal to 1. So this is 1, 2, 5, 13, 34, etc. So write down the Fibonacci sequence and just take the first, the third, the fifth, the seventh term, and so on. Okay? So now you write the quotient of two consecutive numbers in the sequence. So you write an to be gn plus 1 over gn. So you have this sequence. So an, it's not hard to see that this is an increasing sequence. And this converges to the square of the golden ratio. So phi is 1 plus square root of 5 over 2 squared. Okay, so now I can draw the graph of the function, or at least parts of it. So we start with 1. And I told you that, one thing that you can observe is just by volume restrictions that this function has to be greater than or equal to the square root. Okay, so you can't go below the square root just because there is not enough volume. And if you have a symplectic embedding, it's a volume. It preserves the volume. So I can draw the square root, and it's kind of the lower bound for the function. Okay, so by Bursztyn's result, we know that between 1 and 2, you have to be a line of slope 1. So this is 2. And then between 2 and 4, sorry, my graph is a little, I'm not a great drawer, but I'll try to make something that makes sense. So this is the square root. Okay, so between 2 and 4, I'm constant equals to 2. Okay. And then Macduff, notice that 2 is actually a1. So then Macduff and Schlenk said, now you look at, between, for a little bit, this function is going to be linear again until, with slope equal to this guy, basically. So it's actually linear. This line continues through the origin and goes for a little bit until the y-coordinate hits a2, which is 5/2. And then when that hits a2, then it's linear. It's constant again. So you're going to go until this point here, which is 5 over 2 squared. And then you do this again. So now you have another step, another linear step. And this linear step is going to be smaller. And again, the slope is given exactly by the slope that you need to go through the origin. And then you stop at a3, which, I don't know, and then it continues. So then you have another step, and then you have an infinite number of steps. Okay? So this, because of this limit, this is going to converge to some point where here you have phi squared, and here you have phi to the fourth. Okay? And then they also proved that after a point which is 17 over 6 squared, which is about 8 and a little bit, it's less than 9. After this point, the function, well, I actually should use a different color. So this, I'm going to use green for the function. And then after this point, they proved that this function is constant equals to, it's always equal to the square root. And then they also analyzed this interval between phi to the fourth and 17 over 6 squared. It's kind of like these steps are a little tired. They still reappear, but just a finite number of them. So it's like some residual, there are some residual obstructions between phi to the fourth and 17 over 6. But I won't tell you what they are. But you can read, it's in the paper. So it's a very beautiful and surprising result. Okay. So yeah, that solves the question for the ellipsoid in dimension 4. So now we can look at other domains. So what's the next thing you could look at is the polydisk. So yeah, so the polydisk is just the product of two disks. I'm going to call the BA and B of B. So it's the symplectic product of two disks. So this is the set of Z1, Z2, such that pi norm of Z1 squared is less than A, and pi norm of Z2 squared is less than B. So now we can ask what's the Gromov width of this, and what's sort of its co-Gromov width. So what's the biggest, what's the smallest ball that this embeds into? So again, the question of when a four-dimensional ball embeds into this is pretty easy after Gromov. So this is going to happen if and only if C is less than the minimum of A and B. And the converse question actually is a lot harder. So just like the ellipsoid, the converse question is a lot harder. So let me tell you what we know about this function. So this is a long story, and I don't think it's completely understood. So we know that P1A embeds into the ball if and only if C is greater than or equal, if and only if A is less than or equal to C for A between 1 and 2. So it's actually kind of similar to the ellipsoid. So for A not very far from 1, we get strong rigidity. So this is if and only if P1A is contained in B of C. Okay, so this actually is a result by Hutchings. I think he was the first one to show it for all A between 1 and 2. And it was actually known before just for A equals 2 by Hein and Lisi. So Hein and Lisi knew this for A equals 2. And this uses holomorphic curves in a more subtle way than capacities can capture. For A equals 1, you can actually prove this just using ECH capacities or Ecklenhofer capacities. For A between 1 and 2, you really need more holomorphic curves. So Hutchings has a paper beyond ECH capacities where he shows that ECH, there are some curves in ECH that don't show up in capacities, but they're enough to obstruct this embedding. And Hein and Lisi had done that, not using ECH, but found that holomorphic curve obstructions for the case A equals 2. And then Hutchings found more obstructions for A greater than or equal to 2, but it's not, they're usually not sharp. But I will just say one more result about polydisks, which is that for a little bit bigger than 2, we still know the answer. So So if A is between 2 and a funny number, square root of 7 minus 1 over square root of 7 minus 2, which is about 2.54 something. So between 2 and 2.5, or a little more than 2.5, then B1A embeds into BC if and only if C is bigger than 2 plus A over 2. And the point is that, when you get a polydisk, for example, or an ellipsoid to be more to be kind of more elongated, then you can do interesting things that are not, you can definitely see there's no rigidity. So in this case, you can do something called symplectic folding. So you can take your polydisk and you can kind of fold it. So here, I think you just fold it once. And this is a result by Joe Nelson and I think a student in an RU. Huh? Okay, so she's no longer, so she's in algebraic geometry, but this is a beautiful, beautiful paper. Christensen, right? Yeah. And Nelson. So they basically took Hutchins's ideas and squeezed them all the way to get to the right bound. Okay, so you can see this is a very subtle thing, and I don't think that for anything bigger than that, there's a concrete answer. But there are actually a lot of, if you're a student, for example, you could try to take this and move it on. Like there's a lot of combinatorics in trying to understand the sharp bounds. So there's a potential field of research here. What? Sorry, I didn't understand. Oh. Yeah, I don't think it's, I think it's in reason for inch stops there. Maybe that's the magical reason why they decided to. Maybe it's maybe inches and centimeters should be this funny ratio, and they stopped at 2.54. Okay. All right. So, but I want to talk to you about a different set of domains, which is so the first one is what is a Lagrangian bidisk. So here we have a polydisk, but it's just a bidisk, but it's a symplectic product. So one could think about, what if I take the product of two disks, but with a slightly different symplectic form? Or I could do it by keeping the same symplectic form, but instead of fixing the norm of Z1 and Z2, I could fix the norm of X and the norm of Y. So that's what is called the Lagrangian bidisk. So I'm going to actually call it disk, D2, kind of to really emphasize that it's a different thing. And I don't actually need a parameter, as I'll explain. So this is going to be the set of x1, y1, x2, y2, such that x1 squared plus x2 squared is less than 1, and y1 squared plus y2 squared is less than 1. So I'm taking a disk in X and a disk in Y, and I'm taking the product. So each of the factors is a Lagrangian submanifold. It's why it's called a Lagrangian product. And it's easy to see that you don't need parameters, because if I put a parameter here and a parameter here, up to a symplectomorphism, I can make them the same. So, they're all every time, all this, the Lagrangian products of two disks are just a scaling of this one. Okay, so I'll just fix this one guy, specific guy. So the theorem that I proved, and I guess it was published in 2017, is that, actually before that, let me just say that you can compute the Gromov width of this subset. I don't think it was written down before my paper, but it was kind of known by the people who looked at this domain before. So the Gromov width, so the biggest ball that embeds here, so this is if and only if C is greater than or equal to 4. And this follows from a construction of Felix Schlenk and some computations of symplectic capacities by Artstein, Avidan, and Ostrover. Sorry, less than 4. Okay, so Schlenk found a clever embedding, and then Artstein, Avidan, and Ostrover computed the Ecklen-Hofer capacities, or the Hofer-Zander capacities of this domain, and showed that that was sharp. Okay, but I don't think this was written down before. So what I showed in 2017 is that I gave an answer to the opposite, the converse, or to the opposite problem. So if you try to embed this guy into a ball, that can happen if and only if C is at least 3 square root of 3. Okay? And you can actually compute the volumes and see that if you're bored, you can just do a sanity check here and compute the volume of that ball, the volume of this, and the volume of this. So the volume there is going to be 8. The volume of the bidisk is pi squared. And then the volume of this smallest ball that it embeds into is 27 over 2. Okay, so you can check that inequality. So you can check that 8 is less than pi squared. It's less than 27 over 2. Okay, that's not too hard. So let me just tell you what the main new idea here is. So the main new idea is to show that this guy is actually a toric domain. So this guy is symplectomorphic to what's called a toric domain. So what's a toric domain? I think many of you know what it is, but let me just define for those who don't. So for me, a toric domain, I'll be kind of restrictive, but I'll say the following thing. So take a region in the first quadrant of R2, which is defined as the area, so the region between the two coordinate axes and the graph of a function that is decreasing. So this is maybe slightly more restrictive than you see otherwise, but I think this is going to be good enough for today's talk. So omega is the region between the coordinate axes and the graph of a decreasing function phi from 0 a to r, where phi of 0 is positive and phi of a is 0. Okay, you can define this something slightly more general, but this is going to be good enough for today. Okay, so what I proved is that this guy, and I didn't find the toric domain. So the toric domain, so once you have a region like that in R2, then you can define the set of points z1, z2, such that pi norm of z1 squared, pi norm of z2 squared is an omega. Okay? So you basically just take the pre-image of the set by the standard moment map. Okay, so this defines, now you can draw a bunch of different symplectic domains in R2n or in R4, and you can ask lots of questions. And lots are known about these embeddings, especially using ECH, which I'll mention in a little bit. But let me just tell you what domain this is, so before I move on. So this, for the bidisk, the domain, so this guy is symplectomorphic to x omega, where omega is bounded by, is the region bounded by the coordinate axes and a curve which is parametrized by formula that I'll tell you. It's 2 sine of alpha minus alpha cosine of alpha, and sine of alpha plus pi minus alpha cosine of alpha, where alpha is between 0 and pi. It doesn't really matter what the formula is. I just want to show you that it's something very explicit. Okay? So, and I think a couple of things that are interesting about this picture is that it's a smooth curve, which is pretty rare when you look at toric things. I mean, of course, you can draw a smooth curve and ask questions, but a smooth curve appearing naturally in toric geometry is pretty rare. And the other thing that's interesting is that it's a concave, it's what's called a concave toric domain. So this region, so this is a convex function. Okay, so you can verify that from the formula too. Okay. And I want to point out a couple of things about this. The first one is that if you look at the biggest ball that fits here, you can look at the largest ball that's just contained here. So you look at an isosceles triangle like that, and you can ask what number this is. It's easy to compute because we have a formula. And this number is 4. Which means that B4 actually is contained in this toric domain. So that means that the problem of embedding a ball into this toric domain is rigid. So the best ball, I told you, they computed over there, is actually obtained by inclusion. So it's not inclusion of the original domain, because if you look, the biggest ball that actually fits into the bidisk with no modification is the ball with capacity pi. So pi is less than 4. So you can't quite see it here. But once you transform it by the symplectomorphism into a toric domain, then you can see that the biggest ball that embeds is actually the biggest ball that fits by inclusion. So you see that it's not really a rigid problem, but it's kind of rigid after you look in the toric world. So after you put in your toric glasses, then you see the rigidity. And it's kind of one of the points of my talk. Okay? But the opposite problem, which is this one, so embedding the bidisk into the ball, even after you put in your toric glasses, you still can't see the rigidity. So, which is not too surprising. I mean, 3 root of 3 is over here, so this guy doesn't fit into the ball of capacity 3 root of 3. So this toric domain is not contained in the ball with capacity 3 root of 3. Okay? So let me say this one more time. So when you're looking at embedding a ball into the bidisk, or the bidisk into a ball, neither of the two problems are rigid in the sense that the best embedding can be seen by inclusion. But after you put in your toric glasses, then you can see this one, that this one is rigid, but this one is still not rigid even after you put in your toric glasses. So I'm going to make a definition, which is the following. So a symplectic embedding problem is rigid if the embedding exists, if and only if there is an inclusion. And I'm going to say it's torically rigid if these two domains are symplectomorphic to standard toric domains like these, where in the standard toric domains, in the toric domains it's rigid. So if there exists x omega 1 and x omega 2 toric domains such that x1 is symplectomorphic to x omega 1 and x2 is symplectomorphic to x omega 2. And now, if you look in the symplectic world, in the toric world, that x omega 1 into x omega 2 is rigid. Okay? So according to this definition, the problem of embedding a ball into a bidisk is torically rigid, but not rigid. Okay? All the examples I'll talk about, torically rigid is stronger than rigid, but it's not, it's not necessarily stronger. It's just a different concept. Okay? All right. So, and I'm going to say that an embedding problem is non-rigid if it's neither rigid nor torically rigid. Okay, so I'm going to say that this embedding is non-rigid. I wanted to call it flexible, but I think people have different ideas of what flexible means. So I'm going to call it non-rigid today if it is neither rigid nor torically rigid. Okay. So yeah, what I just said is that the problem of embedding a ball into the bidisk is torically rigid. And the problem of embedding the bidisk into a ball is non-rigid. Okay? And I should say one more thing. Being non-rigid just means that you can't see the best embedding by just inclusion in the toric world. Okay? Maybe you could see the best embedding by something else that's easy, like a folding, a symplectic folding or something. But in all the examples that I'll show you in the stock, non-rigid actually means that all the non-rigid embeddings will actually be very non-rigid in the sense that the best embedding is extremely hard to construct. So the best embedding, to construct the best embedding, you'll need McDuff's techniques of blow-ups and using suborbital invariants to construct a non-trivial embedding. So I won't have time to go into that, but I wanted to make that point. Okay, so now let me tell you about a different family of domains that's related to the bidisk. And where we'll see some flexibility and some rigidity too. So, so instead of taking the product of two disks, you could do something different. You could, for example, take the convex hull of the two disks. Or in general, you could take what's called the LP sum of two disks. So I'm going to define the LP sum. So if I fix a P, which is between 1 and infinity, I can define a set XP, which is what's called in analysis the LP sum. So this is the set of, I'm going to call XY in R4, such that the norm of x to the p plus the norm of y to the p is less than 1. Okay? So x and y are two vectors in R2, and I want to emphasize that, again, my symplectic form is dxi dyi. Okay? So this is a deformation of the product. So if p goes to infinity, this guy converges to the product. So you can define, x infinity to just be the product, the Lagrangian product. Okay? So I can tell you what the theorem is. So this is Ostrover and myself, 2019. So there are two parts. The first one is embedding a ball into this guy. So we showed that the embedding of a ball into XP is rigid if P is between 1 and 2, and it's torically rigid if P is greater than 2. And we also found the best values. I'll tell you that later, but the numbers are not extremely relevant. I think the behavior is more interesting. Okay? So it's rigid between 1 and 2, and it's torically rigid for P greater than 2. And I should point out that the case P equals 2, for P equals 2, we just have a ball, obviously. So there's nothing that interesting that happens for P equals 2. You just get full rigidity. So now if you want to do the opposite, XP into the ball, this problem. So this is torically rigid. It looks like we have the opposite behavior. So it looks like it's torically rigid if P is between 1 and 2. And I guess our first guess was that it was going to be rigid for P greater than 2. But actually, so it's actually rigid if P is between 2 and 9/2. And then at 9/2, there's another change of behavior. So after 9/2, it becomes non-rigid. If P is strictly greater than 9/2. Okay? So there's a change of behavior. This is consistent with the result before, which is the case P equals infinity. So that's good, sanity check. Yeah, but I think the most surprising thing for us was how the behavior changed at this kind of random point 9/2. And I'll explain what the 9/2 has to do with it. Okay? So again, the main result is that this domain is symplectomorphic to a toric domain. So the main result is that this is symplectomorphic. Well, this is kind of the main idea. And then we have to do some interesting calculations and use ECH capacities. Okay, so this is symplectomorphic to a toric domain. And the toric domain, I mean, is a little bit harder to write down, but so there's a curve, just like before. And this curve is parametrized by a function that's a bit harder to write than this one. But let me write it down quickly, just so you see that it's kind of concrete. So this is parametrized by, the curve, I'll write it like this. So it's 2 pi v plus gp of v, gp of v for v positive, and then gp of minus v and minus 2 pi v plus gp of minus v for v negative. And not forever, v stops. So the absolute value of v is less than or equal to 1/4 to the 1 over p. So this parametrizes the curve sort of between 0 in the positive sector, it's one formula, in the negative sector is another formula. So this is a C1 curve. Here the derivative is the same, but the other ones don't coincide, which is it's fine because you don't expect complete smoothness just because this function is not smooth. And I have to tell you what GP of V is. It's a kind of slightly ugly formula, but let me write it down anyway. So I wrote it down here. So GP of V is twice some integral. So it's an integral that you can't compute in general. So this is the integral, and where the bounds of the integral are 1/2 plus or minus 1/4 minus v to the p to the 1/2 to the 1 over p. It doesn't really matter what the formula is, but I want to just show you the formula. And these guys are the zeros of the integrand. So the limits are, and you'll see when I explain the proof of this, I'll explain why we get the zeros of the integrand. But it's this formula. Again, if you're bored, you could try to prove that for p, as p goes to infinity, this thing converges to the formula that I wrote before. Okay, so one thing that's very interesting about this domain, the first observation, is that this domain is a concave toric domain for p greater than 2, and it's a convex toric domain for p less than 2. So this is a proposition that this guy is a concave toric domain for p greater than 2, and it's a convex toric domain for p between 1 and 2. And this is one of the key observations. Okay, so I didn't define these things, but let me just say quickly. So a concave toric domain is when that decreasing function is convex, so it looks like a concave thing. And a convex toric domain is when that function is concave, so it looks like a convex thing. Okay, and this is crucial because for those of you who have seen how ECH capacities can be used to prove to find the best embeddings, you probably know that these two kinds of domains have very different behaviors. Okay. So if you know that, you can actually prove part A. No, you can look at the case where p is between 1 and 2, and we can kind of compute everything. So one thing, when p is between 1 and 2, we have a convex toric domain. So it's actually a little bit easier. So if you have a convex toric domain, let me write a proposition, which is basically due to Hutchings. I'll write Hutchings plus, because it's not exactly contained in his original paper, but it basically follows from Hutchings' original quantitative ECH paper with a few more observations, which is that if you have if x omega is a symmetric convex toric domain, then it's pretty easy to compute C1, the first ECH capacity, and the second ECH capacity. So the first ECH, if it's symmetric, just meaning that it's symmetric with respect to the reflection about the x equals y axis. So it's symmetric like that. So you have a point here that I'll call A. So this is the intersection of the curve with the x-axis, which is the same for the y-axis if I assume the domain is symmetric. So it's not very hard to see with a little bit of ECH that the first capacity is this number A. And the second capacity is basically the following. You take the intersection of the curve with the line x equals y, and you multiply that coordinate by 2, or you add the x and the y coordinates. So if this is b, then C2 is going to be 2b. Okay, so this is, if anyone wants to know more about this, I can explain why later. But if you believe this observation, and the ECH capacities, I haven't talked much about them, but I think most of you have heard about them before. They're a sequence of capacities, not normalized capacities. So it's a sequence of obstructions to symplectic embeddings. So now, in this case, what we need to do is we need to compute this A and this B. So A is the set, it's going to be basically 2 pi times 1/4 to the 1 over p. So it's not hard to see that as V, the maximum value here, GP of that is 0. If you plug in V equals 1/4 to the 1 over p, then you get 0 here in the discriminant. So the beginning, the two endpoints of the integral are the same. So this GP is 0, which means that this curve goes here. So the x coordinate is 2 pi times 1/4 to the 1 over p. So that's A is 2 pi times 1/4 to the 1 over p, which looks like a slightly ugly number, but it's actually it's exactly what you need to get rigidity. So using Holder's inequality, for example, you can see that the ball is contained in xp if and only if c is less than this number. So that means that for the problem of embedding a ball in here, we get strong rigidity. So this just comes from C1. Okay, so we get rigidity for the problem of embedding a ball into xp. Okay, and in the opposite direction, if you try to embed this set into a ball, then I told you how to compute C2. And it's pretty easy to see that the ball with capacity 2b is exactly the ball the smallest ball that this domain fits into. Okay, so basically with a similar argument using C2, you get that the toric problem is rigid. So this guy is torically rigid. So xp embeds into BC if and only if C is at least that number C is at least 2b. And if you compute 2b, so what's 2b? 2b is the intersection. B is this x coordinate at the intersection with the line x equals y, which is what you get basically when you plug in v equals 0 at GP. So if you plug in v equals 0 here, the bounds are going to be 0 and 1. And you're going to get the integral of 1 minus r to the p to the 1 over p. So this is going to be 4 times the integral from 0 to 1 of 1 minus r to the p to the 1 over p. And this is nothing else than the area of the disk, the unit disk in the LP norm. So this is the area of the unit disk. Sorry, my drawing is kind of bad. I think you know what I mean. Okay? So you get this number, which is a pretty nice number. So this, it's torically rigid. You compute this number, and it's not rigid. It's not hard to see that the best thing that you can actually embed it into is just a ball of capacity. It's not that one, so it's not rigid, but it's still torically rigid. Okay, so I guess it's more interesting now. Let's look at the case where p is greater than 2 to see kind of what's happening. So when p is greater than 2, we have what's called a concave toric domain, which has a different behavior, and computing capacities is a pretty different game from the convex toric domain. So when p is greater than or equal to 2, we have a domain like this. And now we have to compute ECH capacities of that, we have to use a very interesting technique that kind of goes back to McDuff, which is the idea of looking at a domain and looking at ball packings of this domain. So there is a specific way to fill up the domain with balls that will give you interesting information later. So she did that originally with ellipsoids. So she said, well, if you have an ellipsoid, there's a way to kind of fill it up with balls that will basically be what you need for embedding it into another ellipsoid. So let me tell you what this is. This is called the ball packing. So the first thing is you look at your concave toric domain, and you look at the largest ball that fits there. So that fits by inclusion. So this is basically this. So you take the line of slope minus 1, and you move it until it hits the domain. Okay? So this one you call W1. Okay, so this is your first weight, the first ball. And then you remove this from the picture, and then what you end up, you have something like this. You have two little sectors. And then you apply a transformation in GL to Z to make these two sides straight. So something like 0, 1, 0, 1, 1, and 1, 0, minus 1, 1, or the other way around. And then after you multiply these guys, you put the origin here and you multiply by these matrices, you actually get two new concave toric domains. And then you play the same game. You see what's the largest ball that fits there by inclusion. So you're going to get another number here and another number here. So let me call this W2 and W3. So by induction, you get a bunch of numbers. But then you actually put them in order. So you get W1, W2. Actually, it doesn't really matter that they're in order. So you have a bunch of numbers. Okay. Clearly, W1 is the biggest. And then the next one is going to be either W2 or W3. But it's a bunch of numbers. Okay. So then the first theorem is that this ball packing, so it's not very hard using a few tricks to see that once you get these numbers, that there exists a symplectic embedding of the balls of radius of capacity Wi times 1 minus epsilon, which I'll put very small, into this concave toric domain. So this is a construction that goes back to Lisa Trainer, but I don't have time to go into that. But there exists, you can believe me, a ball packing from I equals 1 to infinity. And the theorem that we proved, so this is by Choi, Cristofaro Gardner, David Frankel, Michael Hutchings and myself, this is from 2015, I think, we proved that the ECH capacities of this domain are given by this ball packing. So it's exactly the ECH capacities of this joint union of balls, for which there is a combinatorial formula that I won't tell you about. But once you write your concave toric domain like this, once you find these numbers, then it's not very hard to compute what these capacities are. Okay? So now, for us, we have a specific formula. And so in particular, actually, C1 is just equal to W1. So C1 is easy to compute, and it's just going to be basically the largest ball that fits here. So kind of by this argument, if you have a concave toric domain, then it's always, the Gromov embedding problem is always rigid, because it's always going to be this ball. And this Wi, this W1, is exactly the same calculation that I alluded to before, is going to be this A of P. So this area of the unit disk in the LP norm. Okay, so this means that the embedding problem of the ball into XP is torically rigid. So now I think if you follow the talk till now, you're probably wondering, what about the other case, which seems to be like where some more interesting things are happening. So what about if I want to embed XP into B of C? So now it's going to depend a little bit on P. So how do you compute W2? So I said to compute W2, you have to take these two domains, and you have to straighten up these edges, and you have to look at the biggest ball that fits there. So that's equivalent to actually looking at the line, taking the line of slope minus 1/2, and the line with slope minus 2, and computing this, the size of this ball here. Okay, so it's a long story, but I'll just tell you that what you get is that that C2 is going to be the intersection of this line with the x-axis. So this point here is the second ECH capacity. Okay? So it turns out, if the slope minus 1/2 is attained, but if you have a graph where the slope is actually not very far from minus 1, if the slope is between minus 1/2 and minus 2, sorry, the other way around. That means the slope is never attained, which will imply that C2 is going to be exactly this point. Okay? So if that's the case, then we have total rigidity, because we can compute this point, and it's again this number, 2 pi 1/4 to the 1 over p, which is exactly what you need for the strong rigidity. So, and then you have to see, like, when does this condition hold? When is the slope not too far from minus 1? And then you do some calculations and you realize that's exactly when p is less than 9/2. So this condition is equivalent to requiring that p is less than 9/2. And then finally, when p is bigger than 9/2, you have something where this is actually attained, and it doesn't fit neither in the toric picture or in the non-toric picture, so it's non-rigid. But actually, it is true that this domain embeds, even in the case p greater than 9/2, it is true that this domain embeds into the ball with capacity C2, whatever C2 is. Okay? So I don't have time to finish to explain this, but I want to say one word about maybe the most important, the part that doesn't rely on ECH capacities, which is the fact that these domains are toric domains. That this XP, both the Lagrangian bidisk and this LP sum, that these are toric domains, and that basically follows from the integrability of the integrable system. So you have, it basically follows from Arnold-Liouville theorem. So you have this Hamiltonian, which is the norm of x, has to do with norm of x and norm of y. So either the max of the two or the LP norm of the two. And then you can find a Hamiltonian which commutes with that, which is the angular momentum. And then you can apply the Arnold-Liouville theorem to basically say that locally it's a toric domain, but you can actually extend. There's no obstruction to extending it. And then when you write down the action angle coordinates, then you get the formula for that function GP that I wrote down before. So there's a little bit of integrable systems there to actually get the toric domains. And then once you get the toric domains, then you can take the ECH toolbox and then make kind of everything work. OK, so I'll stop here. Thank you.